Okay, you see that, you're going to see that. Now look at this animation. As time passes at the same location in space, the electric field is drawing this circle. So if you put your left-hand thumb in the direction of propagation, the horizontal cross the vertical component should give you the direction of propagation, as you see here. That's the clockwise rotation. For the right-hand circular polarization, the amplitude ratio is always 1. And now this time they are 90 degrees out of phase. In this case, again, for simplicity, let's assume that phi x is 0. Then phi y is minus 90 degrees. This time Ex is E naught x and cosine omega t. And for the Ey component, again, you see you have the same magnitude, but this time it starts with sine omega t. In this case, as you see, as time ticks, we turn in the clockwise sense. Okay, so we call it counter ters demek. Counter clockwise or CCW. Counterclockwise or right-hand circular polarization. In this case, if you take your right-hand thumb this time and you put it in the direction of propagation, the way your fingers curl, the horizontal cross the vertical, as you see, will be in the counterclockwise sense. Okay. Any questions from here? Okay. As you see here, as time ticks on the fixed plane, the x and y components move in unison over a circle, and their sense is counterclockwise. They are 90 degrees out of phase with each other. Any questions from here? Okay, so the elliptical polarization is the most general case. You can have any ratio of A or any phase difference. As I mentioned before, elliptical, the circular and linear polarizations are special cases of elliptical polarization. So depending your amplitude ratio, you can have any type of ellipse, and depending on your phase difference, you can have a left-hand or a right-hand elliptical polarization. For example, in this case, you have the elliptical polarization, the right-handed elliptical polarization.
Hocam 90 ya da eksi 90 olduğunda circular polarization olmuyor muydu yani? Ben mi yanlış hatırlıyorum?
90 ya da eksi 90 olursa ve A eşittir 1 olursa circular polarization olur.
Anladım, tamam.
İki tane condition'ımız var yani. Okay. Başka soru var mı? Okay, so this is a left-handed elliptical polarization. These are examples. As you see, we trace out an ellipse. Okay, so this is a difference. The animation shows you the circularly polarized plane wave versus linearly polarized plane wave. E and H components. This polarization is also used in, this is a circularly polarized wave again, in optics. And a circularly polarized wave can be written as a sum of two linearly polarized waves. This is a very important application, as you see, at any given time. So even though you have a circularly polarized wave transmitted from your broadcast station or from satellite antenna, you can receive it with a horizontally oriented or a vertically oriented antenna. Okay. As you see, at any given time, you can have a field on those components, which makes it easier for us. So the way that we're going to decompose it is in this way. For example, you have the linearly polarized wave, and that can be decomposed into two components, as you see here. And the linearly polarized wave, AX, can be written as the sum of a left-hand circularly polarized and a right-hand circularly polarized wave. At this point, okay, the application of this is in communication, in HF communication. Let me denote that. Let me see if we have one more slide. Okay. Okay. Now what happens is, bu nasıl oluyor, nerede kullanıyoruz? Şimdi onu göstereceğim. Okay, the HF band is 3 to 30 megahertz range. In this range, what we call skywave propagation is the main medium of propagation, the mode of propagation. So this is Earth's surface, and you have a transmitter here, and you have a receiver which is at least 500 kilometers away. Okay. In the atmosphere, you have layers. You start with troposphere, which is about 10 to 12 kilometers in altitude. Over it, you have about to 25 kilometers, you have stratosphere, and about 40 kilometers, you have the what we call the mesosphere, and around 50 kilometers, you have the ozone layer, which protects you from the harmful layers of rays of sun. The ozone layer, ozone is O3. And over it, the ozone layer protects you from these sun rays, but the atmosphere, which is quite dispersed, the gas, is unprotected. So extreme ultraviolet and X-rays will going to heat up the atmosphere over here. And typically your atoms or molecules, which will be circulating in unison and happily around it, we're going to get this extra, sorry, radiation, and it will be, you're going to left with an ion, heavy and large ion, a positive charged particle, and a free, light, and very fast electron. Okay, so this phenomenon denotes the fourth phase of the material. Okay, so you have solids. You heat up the solids, it becomes a liquid. If you heat up the liquid, it becomes a gas. If you have a gas, if you heat it up, it will going to be a plasma. Okay, so this medium is called a plasma medium. Your TV screens, plasma TVs, are made up of this property. Okay, this is the fourth phase of the material. So over 50, 60 kilometers over the ozone layer, the atmosphere becomes a plasma. Now, most of the cases, this plasma is isotropic. The ones in your laboratories and so on are isotropic. But in Earth, Earth has a magnetic field. We call it geomagnetic field. Because of this geomagnetic field, we call this magnetoplasma this time. The medium in this, what we call thermosphere, ısıl küre. Niye öyle diyoruz? Because it gets very hot. It's more than 2000 kelvins. Okay, the magnetoplasma becomes anisotropic due to the Earth's magnetic field. In this case, your D, displacement, is related to your electric field through a matrix. Okay, your epsilon is not a number anymore. It becomes a matrix. Because of this, the polarization, the material polarization inside the system is, or conductivity also is a matrix. Okay, and in this case, the wave, as you transmit one wave into the ionosphere part, that's why we call it ionosphere, because it's filled up with ions. It's a plasma environment. This is ionosphere. Okay, the wave that is transmitted into the ionosphere splits into at least two rays. Okay, one of them is called ordinary wave, and the other one is called extraordinary wave. Okay, and these two waves have different k vectors.
Hocam peki yansıma oluyor mu?
Anlayamadım.
Yansıma oluyor mu peki, yansıma?
Yansıma ya da kırılma ya da tam kırılma diyebilirsiniz. Ama ilk önce iyon küreye girdiği zaman iki tane ayrı k vektörüne ayrılıyor. Bu iki tane k vektörüne ayrılması sırasında mesela burası linearly polarized bir şey gönderdiyseniz buradan, bunlar left hand ve right hand circularly polarized ve right hand circularly polarized olarak iki farklı polarizasyona ayrılıyorlar. Yani sadece k'leri ayrılmıyor. Aynı zamanda linearly polarized dalga bir left hand ve bir right hand circularly polarized'a karışıyorlar. Bunların içerisine travel ettikleri zaman, when they travel inside the ionosphere, as you see, they have different propagation constants. They have different directions. So these two waves with the same information, they have both the same info. That's the critical part. Same info in them. They travel from different paths with different time delays. Okay. In communication, this is called a multipath problem. And as the wave propagates, they will going to have different polarization differences. So as they exit, now I'm going to explain how they are going to exit from the ionosphere. When you sum them up over an antenna system, they're going to have these phase differences between them, and your original linearly polarized polarization will be rotated. It's called Faraday rotation. So your phase plane, your polarization plane will be shifted. Okay, And how they're going to travel in the ionosphere, the critical parameter of the plasma is the electron density. And the characteristic frequency of the plasma is called the plasma frequency. It's made with Ne, the charge of the electron squared, divided by mass of the electron times epsilon zero. Okay, that's called the plasma frequency. So if you write it in terms of linear frequency, not the angular frequency, this is about 9 times square root of Ne. Okay, so the wave frequency that you have will going to propagate inside the medium. This is the isotropic case, but it will going to give you an idea until your wave frequency matches the plasma frequency. Okay, when the wave frequency matches the plasma frequency, this will be 1 minus 1, n will be 0. If n is 0, then k will be 0. If k is 0, the wave cannot propagate any further. Okay, e to the minus jk dot r. Okay, this will be e to the 0. E to the 0 means 1. The wave will not be able to propagate. What will happen to the energy? Enerjinin korunumundan nereye gidecek peki? So it will going to bend back. Okay, so some people call it a reflection. Some people call it a refraction. But what happens is, biri kırılma, biri yansıma. It will going to reflect back. Okay, when it reflects back, okay, the energy is turned round. So within the skip distance of 500 kilometers to thousands of kilometers, you can communicate over the conducting layer of ionosphere. Okay, that's in the HF band, high frequency. In Turkish, we call it kısa dalga, KD. Tamam mıyız? Now, in microwave, we use ferrites for phase shifters. This time, B, the magnetic field, is related to H. This is the isotropic case, but in ferrites, this time mu becomes, as you see, a matrix. Therefore, B is not parallel to H anymore. So if you have a slab of ferrite like this, and if you send a wave inside to the ferrite, depending on the length of the ferrite, the polarization that you have sent in here, we're going to have a phase shift or a polarization plane rotation, the Faraday rotation, and the phase will be shifted compared to this one, the one that enters and exits. Polaroids in optics also use the same phenomenon. So these polarization shift carries information in various applications, especially in sensors. Okay, so for Polaroids, for ferrites, for ionospheric HF propagation, for HF communication, this phenomena, polarization shift, is very, the meaning of it is very important for us. The application has lots of important applications. Okay.
Hocam bir şey sorabilir miyim?
Sorabilirsin.
Bu yukarıdaki n değeri sıfıra eşit olduğunda hem reflection hem refraction mı oluşturabiliyor demiştiniz?
Reflection diyen de var. Sanki gidip ayna yansıması gibi geriye dönüyor. Yani sanki oraya bir conducting plane koymuşsunuz ve daha fazla wave gidemiyor ve geri dönüyormuş gibi. Bazıları ise oraya refraction diyor, kırılma. Çünkü kırılma indisi 0 olduğu için wave daha fazla ilerleyemiyor. Ama sonuçta wave geri dönüyor. Yani daha fazla ilerleyemiyor. İlerleyen dalgaları evanescent wave, ilerleyemeyen dalgaları evanescent wave diyoruz. Diğerlerine traveling wave diyoruz. Şimdi yansıma ve kırılmaya başladığımız zaman onları daha iyi anlatacağız.
Tamam,
Propagating wave ve traveling wave. Burada 3 tane temel dalga tanımlayacağız. Propagating wave ve traveling wave diyoruz. Duran dalgalarımız var. Waveguide'ın içerisinde propagation direction'a dik olan yönlerde onlara standing wave diyoruz. Ve aslında faz propagasyonu olmadan amplitude'u zayıflayan dalgalarımız var. Öbür tarafa geçemedikleri için ona da evanescent wave diyoruz. Okay.
Tamamdır hocam, teşekkür ederim.
Rica ederim. Şimdi burada bir örneğimiz var. For example, bu example'ı görüyorsunuz değil mi?
Evet hocam.
Tamam. Heh. Allah'ım yarabbim gene buraya geldi. Niçin böyle yapıyor? Peki. Yani gitmeyecek başka türlü. Şuradan koymayayım. Buradan takip edin, olur mu? For example, E is given to you as JAX plus AY e to the minus JKZ. Her zaman time domain'e dönün. Burayı takip edemiyorsanız phase difference'ları vesaireyi, tamam mı? Şimdi gördüğünüz gibi bir kere nasıl bir polarizasyon? Bakar bakmaz bir kere bu ya elliptical ya circular bir polarizasyon. Bir kere neden? Çünkü burada iki component var. İki component'ın magnitude'u birbirinden aynı. Bir. Phase difference'larına bakacağız. Eğer phase difference'ları artı eksi 90 derece ise o zaman bu circular polarization. Yani bakar bakmaz görüyorsunuz. Ama emin olmak için ilk önce bunu yeni başlıyorsanız çevirin. Time domain'e çevirin. Time domain'e çevirmek için ne yapıyoruz? Buradaki dalgayı alıyoruz. The phasor form E of Z. And we multiply it with e to the j omega t and take the real form of it, like here. So, in this way, we are concentrating on this part where AX and AY components exist. J can be written as e to the j pi over 2, and in the real form, it is written as cosine omega t minus kz plus pi over 2 plus AY cosine omega t minus kz. Now, electric field, Z is equal to 0 t, that's equal to AX cosine omega t plus pi over 2 plus A of A hat of y cosine omega t. As you see, we write it as minus sine omega t, cosine omega t. So the EX component has the minus sine omega t, and the EY component has the cosine omega t. The propagation direction, we check again, is in the, burada bazen hata yapıyorsunuz. Onun için çok dikkat edin. Mesela bu propagation direction'ın pozitif z yönünde vermişiz. Bazı sorularda mesela eksi z yönünde veriyoruz. Her zaman şuradan çıkan, bunu orient edeceğiniz şey artı z ise artı z, eksi z ise eksi z, önemli değil. Ama propagation direction'da olmalı. Hata buradan kaynaklanıyor. O zaman sensin tersini buluyorsunuz çünkü. Ezbere burası z, burası x, burası y diye çizmeyin bunları. Anladınız mı dediğimi? Şuraya çizdiğiniz her şey mutlaka propagation direction yönünde olsun. Ve şuradaki componentları da bu propagation direction'a verecek şekilde orient edin. Dediğimi anlamayan var mı? So you start with omega t is equal to 0 and you turn, okay, with your right hand. The propagation direction is in the right hand thumb direction, and I circle my hand, so it's counterclockwise or right hand circular polarization. Any problems with this one? Sınavda çok vaktiniz oluyor. Onun için lütfen emin olmuyorsanız oturun, şu omega t'lere değer vererek tek tek çizin yani. Bu çok zor bir şey değil. Yani şunu yaparsanız 20 puan alacaksınız. Yapamazsanız 0 alıyorsunuz. Anladınız mı? Üşenmeyin yani. Niye üşeniyorsunuz anlamıyorum. So in this example, for example, 1 plus j ay plus 1 minus j az. And this time the propagation direction is plus x direction. Okay, so I'm going to orient my y and z axi in a way that their cross product with respect to your right hand should give you in the positive x direction. Okay, and then I represent them in the phase terms. So 1 plus j and 1 minus j have the same magnitude, square root of 2, but their phase differences are different, as you see. So this has pi over 4, 45 degrees, and the other one has a minus 45 degrees phase shift here. E to the minus jkx times e to the j omega t, take the real of it. So you can write the ay component and az component with respect to their phases. At x is equal to 0, at a fixed point in space, you're going to have the y component and the x component. So at omega t 0, you start with the z component, as you see right here. Omega t is equal to pi over 4, you move here, and then you move there, and then go back to 2 pi. So as you see, this is again a right-hand circular polarized wave or counterclockwise sense. Any questions from here? Okay. This is example 2. Example 3. This time you have 2 plus jax and 3 minus jaz, e to the minus jky. E to the minus jky means you are propagating in the plus y direction, and you have two components, x and z. And again, make sure that you draw these in order to have the k vector coming out of you. Hep böyle çizerseniz yanılmazsınız. Öyle ki z cross x y'yi verecek. Tamam mı? Yani horizontal ve vertical componentlara koyduğunuz şeyleri her zaman bunların cross product'ları y'yi verecek şekilde right hand kuralına göre çıkacak şekilde yapın. And then you find their magnitudes and phases, and then take the real form of it. You have the x component and the z component. As you see, this time the amplitudes are different, and there is a different phase shift than 90 degrees. Therefore, that's an elliptical polarization. And as omega t moves in time with a fixed point in space, you see that this time you have the left-hand orientation, and this is left-hand elliptical polarization. Its sense is clockwise this time. Ezbere hiçbir şey yapmıyorum gördüğüm gibi. Circular, elliptical polarization with the clockwise sense. Any questions from this example? Okay, my fourth example is JAX plus 2JAY e to the minus JKX. You see that they have the same phase, but different magnitudes. You can immediately tell me that it's a linear polarization because they have the same phase. They are in phase with each other, as you see, and their magnitudes are different. Therefore, A is equal to 2, phi is equal to 0. So this is the left hand, linear polarization. Okay, you move in this direction. Any questions from here?
Hocam bir şey sorabilir miyim?
Sorabilirsiniz.
Bu örnekte propagation direction'ı eksi z yönünde mi oluyor?
Aynen öyle oluyor, evet.
Peki çizdiğimiz şeyden bunu hani eksi z'yi bize gelecek şekilde çizersek y ve x'in duruşu yanlış olmuyor mu? Yanlış mı düşünüyorum?
Evet ama bu circular polarization, elliptical polarization olmadığı için aralarındaki faz farkının bir önemi yok. Bunun bir sensi yok yani.
Peki tamam o zaman.
Yani burada şöyle gitmesi lazım. Yani bunu çizdiğiniz zaman bu içeri doğru gidiyor. Ama burada linear polarization olduğu için sensi yok ya. Onun için ona göre çizilmemiş.
Tamamdır hocam. Teşekkürler.
Rica ederim.